We are going to spend the next hour going deep on DSPy, not just what it is, but why it exists, how it thinks about the prompt engineering problem differently from everything else out there, and how to build real pipeline with it. We will compare DSPy side by side with traditional prompting on some of the examples, and you can see exactly what you are trading and what you are gaining. We will build 5 complex programs: a classifier, RAG pipeline, a multi-step reasoning chain, a self-correcting agent, and finally we will run the optimizer and watch how the SPY rewrite its own prompts to beat a handcrafted baseline. If you have watched the short intro video, this picks up where that left off. If you haven't, don't worry, we will cover the fundamental properly before going deep, but you can have a look at that video to have a basic understanding about what DSPy and the installation and how to start with a simple program in DSPy. Here is a real prompt from a production code base. This was written to classify customer support tickets. You can see here in the prompt that you are assigning a system role for the LLM. You're telling him that you are expert customer support, you're giving some kind of important instruction, some examples, and some expected output. This took someone probably a couple of hours to get it right. It has 7 structured decisions backed into it. As I mentioned, so there is something about the persona, the instruction to think carefully, the JSON format requirement, the category list, the urgency scale, the few shot examples, the ordering of those examples. And here's the problem. Every single one of those decisions was a guess. Does the persona actually help? Does think carefully wording improve accuracy or just waste tokens? Are those 2 examples the best 2 examples, or would different ones work better? Should the examples come before or after the instruction? And all of these kind of questions about the prompting. Nobody knows. You test it once, it seems okay, you ship it, and you never revisit it because you didn't have a systematic way to improve it. Now here is a DSPy version of the same task. We can see here the ticket classifier, which inherits from the DSPy signature, and there is a one input field which is a ticket, and the other output fields like category, urgency, and reasoning. And that's it. No persona, no formatting instruction, no examples, no think carefully wording, just hear what goes in and what comes out. This version can be optimized also. You can give DSPy some labeled examples, metric function, and it will figure out better examples, better instructions, better ordering than you would do by hand. It treats the prompt as a compiled artifact, not a thing you write. Before we write any code, let me give you the complete mental model. This will make everything that follows make sense. DSPy has 4 layers. Understanding all 4 is the difference between using DSPy as a fancy prompting library versus using it as it was actually designed. So the first layer is the signatures. These are your data contracts, input field, output field, one-line description. This is where you describe what you want without saying how to get it. Think of it like a function signature in a typed language. You declare the interface, not the implementation. The second layer is the modules. These are the building blocks that turn signature into LLM call. Predict is the simplest. It's just one call and direct answer. You have chain of thought, adds reasoning before the answer, reacts, adds tool use. The model can search, calculate, look through, look things up. You have program of thought, generates and execute codes. You compose these modules the same way you would do with functions. One module's output becomes another module input. The third layer is programs. When you combine modules in forward method, you get a program. This is just a Python class. The DSPy magic is that every prompt decision inside that program, like which examples to use, what instruction to include, whether to use chain of thought, is actually a parameter that can be optimized. Just like neural network weights as parameters that get updated during training. Your prompt decision are parameters that get updated during DSPy optimization. The fourth layer is the optimizers. These are called teleprompters internally. You give an optimizer program, dataset, and metric function. It runs experiments, trying different examples, different structure phrasing, and updates the program's parameter to maximize your metric. The result is compiled program with optimized prompts that you can save, version, and deploy. The analog is that make this click. Writing prompt by hand is like writing machine code by hand. It works, you can do it, but the moment you have a compiler, which is a thing that takes higher level description and produces optimized machine code, you stop doing it by hand. DSPy is that compiler for LLM programs. Okay, let's get the environment set up. We are using Olama for local interface. Same setup from the last few videos about Olama and DSPy introduction. You can have a look from the links in the description below. But as a short summary, you can here call poetry add. So I'm using poetry for my environment setup in this Python project. So you can do poetry add DSPy and then install that package. For this project, I will use Chrome DB and sentence transformers, which you can install also using poetry or using pip install into your project. In this project, I will use Jima model from my Olama list. So I have in my list few models. So I will use a Jima 3. You can use any model from your installed list locally, or you can use GPT models if you have the OpenAI key. I will start by adding a new file. So I will just call it here deep dive DSPy, and then I will just copy paste some of my prepared code here. Here just prepare the configuration for the DSPy and just instructing to use the Jima model from my Olama localhost setup. For the first program, which is a sentiment classifier, we will be building the first traditional way, then we will just do it the DSPy way. So you can see the comparison directly. So the first version, which considers a traditional way of doing prompting, it will be something like this. So you will have the prompt. As we mentioned, it will contain all the instructions, the role specification for the prompt. So you are an expert text analyst, and then give you some rules and the JSON format for the expected output. And the classify traditional function is actually just creating the client, as we know that the Olama is just using the OpenAI specification, so we can have the client pointing to our Olama setup using the model that we need, and then having the review message as a request, waiting for the response. And we can see directly here that what we are doing with JSON parsing. So we have a defensive JSON parsing, so to say, stripping the markdown code blocks, because the model sometimes wraps JSON in backticks, even when you tell not to do. And there is an error case where the model just ignores your format instruction entirely and just returns something unusual. So you have to handle this kind of error cases. And now if I just copy paste the code block that represent the DSPy way of doing this kind of prompting, we can see here that I would have just a class called sentiment signature, inherit from signature, and I will have one input field, which is a review that I need to classify. And then I can just define the output field, which is sentiment, confidence, key phrases, and reasoning. And each one of them, I can put the description that I want for that field, and just here specifying if it is input or output field using the DSPy library. So I'm using the chain of thought here for this sentiment signature, and then I'll just create a function that will take a review and call that DSPy classifier on it. So to put everything side by side, I will just paste here the example code. So I have a test reviews. So I have 4 reviews. Actually, I can just add an empty one to see how the both ways the traditional and DSPy deals with this kind of empty input. So for each input of the review, the classify or the classifier, the traditional and the DSPy way will just decide what could be the result, and we can see somehow how the different will be between both of them. Just keep in mind that DSPy, we didn't supply any kind of prompting. We just supplied a structured class, and we will see that how the behavior will be very close or even better than the prompting or traditional prompting way. So if I just run here the example, I need to type Python, then deep dive DSPy. So we can see here the results. Actually, maybe the first two reviews, it could be obvious that we are speaking either in a positive or negative way. So the laptop is absolutely incredible. The second one is arrived damaged and the customer service ignored my emails for 2 weeks. So this is a review. So one of them is positive and negative. I guess if I can jump directly down to the DSPy results, so I can see also here is a positive. The first one is positive, the second one is negative. So we get similar result. So this also at least will give us some kind of baseline that DSPy also is not worse than the manual prompting, but we can see how it differs in in the other reviews. For example, the one with the battery life is terrible, but the screen is gorgeous. So we have here a mixed sentiment. So we are saying it's terrible, but also we are saying some positive words about the screen. And in the traditional way, I think the prompting wasn't helping to get a result. This also depends on the model, of course, but here in our case, it didn't give any result. If we look in the DSPy, we see that we got some kind of result. We got a negative result, and the reasoning here explaining that because of the word terrible, the negative aspect is quite strong, which is because of the word terrible, which leads to overall slightly negative classification. So at least it gives us some kind of result and some kind of judgment and reasoning. Also, when we just applied dot in the review, which is also could lead to some kind of empty result from the LLM, because we need to tweak the prompt to deal with this kind of input, but we can see how fast the DSPy dealt with it. So we can see here when we supply dot to DSPy, it's give us a neutral, and it gives us the reasoning for why it's giving us this kind of sentiment. And it's saying here the review consists of single period, and here just saying that this is just a neutral sentiment. So it gives us just a reasoning, whether it's right or wrong. It's just a reasoning. It could be, of course, hallucinated because it's using LLM, but we are speaking here about how close it will be to what expected as a behavior. And again, everything here you see is being structured and handled by DSPy without any kind of extra coding or boilerplate coding from our side to deal with any kind of response for the LLM. As we know, the LLM response will be in a textual form, and DSPy even hide this kind of response structure handling from us. So the second example, we will deal with the RAG program. So I can put here deep dive RAG DSPy as our new example. It will be about RAG pipeline, the retrieval augmented generation. So you have a document collection, a user asks a question, you retrieve relevant chunks, the model answer using those chunks. The traditional approach to this involves a lot of prompt gymnastics. How to tell the model to use only the retrieved context. How do you format the context chunks? What do you do when the answer isn't in the context? So we can build this using the DSPy way and see how it handles all of this. So first, I will just also copy my prepared code here for preparing the document setup. So here we have a simple local document store from ChromaDB. And we can see here we are initializing it with a few documents, which is a list of knowledge base, a list of textual knowledge base about Python, global interpreter log, and some other list comprehensive or generators and decorators. So it's just a small knowledge base about Python. And here we're just adding the documents, all the documents to our document collection that we created here above using the Chroma client. So the second step is just creating the drag structure using the DSPy. So I think I need to install here DSPy or bring DSPy to our program. So we have here the retrieve function, which is trying to retrieve a relevant document for the query. And this is getting it from the document collection that we created earlier. And then we have the generate answer class, which is a signature DSPy class having the context and question as input fields. And then we have the answer, confidence, source used as output fields. And here we have the RAG program, which is a DSPy module. So the generate function will be a chain of thought. So the DSPy chain of thought program. And we will retrieve the context using the question and then generate the answer. I think here I just need to initialize my LM connection for the DSPy. So I've just prepared here, paste it. So again, here I'm using the local models. After that, I think we just need to test it against some test statements. Again, I copy here my prepared questions. The last two question is something that is not exist in our document or in our doc collection. So we need to test here how our DSPy dealing with the questions that actually not exist in our knowledge base that we are supplying it as RAG. And we need to see if it will retrieve result or what's the reasoning that it will be for this kind of results. So if I call this program here, so we have the deep dive drag example. So here we have everything is being answered. We can see here while creating the DB of our documents, you see here that there's something is unexpected happen. The warning about the embedded position IDs being unexpected, you can just ignore it completely. That's just a sentence transformer library loading a paired model and noticing that one key in the wait file doesn't match the expected architecture. It's not an error, nothing is broken. The embeddings work perfectly fine. This shows up anytime you load this all mini LM L6 version 2. And it's been known cosmetic warning in the library for years. The 100% load bar above is what matters, so waits loaded successfully. And actually here you can, if we ignore the first few questions and everything is used by the context, you can look directly in the last two questions that we marked here that they are not in our documents, like the capital of France and when was Python is created. The model correctly reports low confidence and source used is false. So because the retrieved documents weren't relevant, it doesn't hallucinate. With the traditional approach, getting this behavior require explicit prompting in structure, like, for example, adding the warning only answer from the provided context. If you don't know, say I don't know, something like that. And even then, models regularly ignore it. The DSPy output contract plus the chain of thought reasoning makes this far more reliable. Now here's something worth pausing on. The context field takes a list of strings. If we go back to it, so here the retrieve, so here's the context, get what is the output of retrieve, and the retrieve is giving us a list of strings. DSPy handles the formatting of that list into the prompt automatically. In the traditional approach, you would write something about like joining all this kind of list inside the prompt and wonder if that's the best format. So here DSPy, once you are just putting it into the generate function, which is a chain of thought, you just completely don't care about how this will appear in the prompt. In the third program, we'll discuss the multi-step reasoning chain. And here's where DSPy start to feel genuinely different from everything else. We are building here a multi-step reasoning chain for code review. something that needs to analyze the code on multiple steps before producing a final assessment. The traditional way of doing this is either one giant prompt with all instruction crammed in, or multiple separate API calls with manual context threading between them. Both approaches are brittle. So first we'll start with the traditional multi-step, let's say the ugly version. I will just here create a new file for our demo. Let's call it deep dive multi-step. And I will just paste my code that I prepared for the traditional code review. So basically here in this function, we are going step by step in reviewing the code. So we will have the code as input. And of course, we prepare our client for the local Olama. And the first step is analyzing the code. So we need to give the issues prompt and try to instruct the LLM to analyze the code and supply the code within the prompt. And from the response, we need to get the issues. The second step will be the severity check or the severity prompt that we need to give it to the LLM and supply with the issues and try to find how critical the issues are, or just classify it as critical, major, minor, clean, and something like this. Getting the output out of the severity response, we need to do the last step, step 3 of fixing the code. And here we need to supply the code, supply the issue and severity, and waiting for the response, which will be the fixed or the final code. And this will be the traditional way of doing it. We already notice here we have multiple LLM calls, so multiple API calls, at least 3 calls here we are doing in this function to get the final response. Now the DSPy version, again, I will just copy paste my prepared code here. The DSPy version will have the following structure. So we have a separate data structure for each step. So for the first step, the identify issues, we have a separate data structure with the input, which is the code, and the output will be the issues and an indicator if it has issues or not. So a Boolean indicator. And then the second data structure is the severity check. So assess severity will be a separate object. Also will have the code as the input and the issues. And then it will output the severity and the severity reasoning. Also, we will have here the generate fix data structure, which again will get the original code and the issues and the severity and try to output the fixed code, also the changes being made to the code. We will have also another data structure to suggest improvement. Again, we have the code and fixed code, and then it will tell us what the improvement that has been done. For our program, the code review pipeline, which is a module, so we will have the following setup. So first we have the identify as a chain of thought. As we mentioned earlier, chain of thought will help us to add the reasoning, and the assess will be more or less a direct predict using the assess severity data structure we defined earlier. And then we have the fix, and the fix because there is also reasoning out of it, so we see as a chain of thought. And the improvement, more or less again, it's just a predict because we are trying to predict or output the improvement that done to the original code to reach the final code that we fixed. And here's the actual program or the steps done inside the forward. So the first step is getting the issues, and here we have just like a small check. If we don't have any issues, just continue with a final prediction. If we have issues, we need to check the severity, do the fixes, and also call the improvement. And the final prediction will have all the output from the issue, severity reasoning, and also the fixed code changes and the improvement. So here I just prepared also buggy code or the code that have issues, and this code will be tested against the traditional way and also the new way using the DSPy. So this code contains three functions. We can see here the first function, import the SQLite and do the connection, call the query, return the data. We have another process item function, which is so getting all the input items and just try to append the result by duplicating each item. We have the calculate average starting from 0 and then trying to sum up the total divided by the length of the numbers. So the first check will be from the code review by DSPy. So just write here DSPy code review pipeline, and here will be the traditional code review pipeline. I'll try to run the program. So we have deep dive, multi-step, DSPy. Here I think I just forget to set up the NM configuration for the DSPy. So I'll just quickly add it to the top here. Will be the same module that we are using for our examples. And then we just run the example one more time. So we have now the result of the both version with DSPy and with the traditional way. So with DSPy here, it found already the issues. So the SQL injection issue in the first function, and the get user data, and also the non-Pythonic iteration in process items. I think here it's more about using the list comprehension here, and it gives us also the severity of that issues and the reasoning behind that, especially for the SQL injection vulnerability. Also, the second steps is giving us a fixed version of the code with all the changes that will do check, with all the changes that will solve the vulnerabilities. For example, importing the SQLite outside the get user data function. So not with every call to the get user data, we are importing that functionality and using it. And here with all the suggested improvement. In the traditional way, we also found the issues. It's also found the injection vulnerability and many other issues, and also try to fix it relatively the similar way that how the DSPy version does. I think the main difference, if we put aside the issues that have been discovered between the both traditional way, that with the DSPy version you already specified as minimum as possible or no prompting at all, just defining the DSPy objects structure and what you are trying to do in the program module, and it's already get some kind of enhanced version of the code. In the traditional way, we have a similar behavior, so it did it in the same way, actually finding also the SQL injection issue, doing the import outside the function, and getting some kind of enhancement in the process items and the calculate average. So basically the issues that is being found by not having prompt at all and just a structure is almost similar to what you can do with a prompting. So as I mentioned in the beginning of the video, that the prompting engineering could take us more time to find the best prompt to solve some kind of issues, but with DSPy it's faster, and we can see in the next or after the next example how the self-optimization for the prompt could take this even further. So in the next example, we'll discuss the DSPy reason and act loop. So the React module, which implement the reason and act loop. And in the reason and act loop, the model decide what tool to call and call it, observe the result, and continue reasoning until it has an answer. So I will just create a fresh new file here. So we just call it deep dive tool call DSPy. The key difference from the other framework that have this kind of tool use is that the tool calling logic is a DSPy module, which means it is also optimizable. The model learns when to use tools and when not to. So let's build simple agent that can calculate things and look up information and documentation. So I will have this prepared code here. Like always, I need to import the DSPy. So here retrieve will use the same retrieve rag DSPy that we created earlier. So we created in the rag example, we created a documents collection that have all this kind of information, and we have the retrieve function that will get out of that collection an answer for our query. So we will use that one also in our tool call. So I'll just retrieve it here. And we will just look back into our new tools. So the first tool is a calculator. So here we are just having some kind of simple mathematical expression, just simple operations, and we are having some kind of check to see the allowed operations or allowed digits in that operation and execute it, just evaluate it. Also, the second tool is just getting something from our docs and retrieve it using the query call and see if we get answer from our documents DB. The last tool is checking the code syntax. So here we're just getting the AST, the abstract syntax tree, and just check if the syntax is okay or there's any kind of errors. So now the agent that we define using the SPY is a Python helper signature in our case here, which is just a signature having the question as the input, and the output will be the answer and the tools being used to get that answer. Now we can create our React agent. So the React agent will have that signature as a base model, and then we will supply all the tools for that React signature. And of course, we have here some kind of cap for the iteration. So we have the max iteration is 5. Now here I have just prepared some kind of questions, and we have the tool call. So we can see here the questions are a little bit simple. So the first one, what is 2 to the power of 16? So here we're mainly asking about the first calculator tool to be called. And the second is about some kind of documentation. We are asking that how do Python generators save memory compared to lists? And the third one here, does this code have a syntax error? So here obviously we are trying to have the call to the third tool, which is like a syntax check. The last one we see here, if I have a list of 1,000 integer and user generated expression versus list comprehension, roughly how much less memory does the generator use? So I think here also this calculator tool, we can see after executing the tool here what could be the result. But before that, I guess we need to initialize, like always, the LM configuration for the DSPy. So I'll just put it here again and then try to run the code. So we have Python deep dive to call. So we can see here how the tools being called. So for example, the first question is giving us the answer and telling us the tools that is being used. And in this case, the calculator. The second question is about like having something from our documentation. The third one is like checking the code syntax. So it's just precisely giving us which tool is being used and giving us the answer from that tool. Also, the last question is using only the calculator. So the last tool is using the calculator, for example, and it giving us not only the answer, but also the explanation about it. So in the last example, we will discuss the optimizers. So I will create an example file for the optimizer. So deep dive optimizer DSPy. Everything we built so far give us a nice introduction about DSPy, but it's still essentially manual. We wrote the signature, we chose which module to use, we designed the pipeline, DSPy handled the prompt detail, but the high level decisions were still ours. Now we get to the thing that makes DSPy genuinely different from everything else, the optimizer. This is where DSPy earned the name, so declarative self-improving Python. We are going to take our sentiment classifier, give the optimizer some labels, example, and metric, and watch it rewrite the program's prompt to perform better than our hand-designed version. So first we can just give some training data. So I'll just here copy paste some training data and import the DSPy. Basically here we are just giving some kind of sentiments, and we know what sentiment it is for that reviews and the confidence level. So we are giving all this kind of training data to our DSPy. So we have the training set and we have the validation set, like any normal machine learning training process. So we will create the metric file that this PY needs it. So here, so I will copy paste the metric functionality here. So we have a sentiment metric. So here we need to measure how accurate we are against the expected output. So the prediction from this PY against the expected output. We will create a baseline classifier. So I just need to import the sentiment classifier from our original example. So here's the baseline performance. This block measures how well the unoptimized classifier performed before DSPy touches anything. It's our starting benchmark. For each review in the validation set, it runs the classifiers, scores a prediction against the expected output using the metric function, then averages all these scores. That average is the number that we will compare against after optimizations run. Without it, we would have no way to know if the optimizer actually helped or not. So this is just establishing the baseline. Run the vanilla classifier, score it, remember the number. We needed to prove the optimizer did something. So now actually here I will paste the optimizer. So here we need to configure the optimizer. The bootstrap view shot is the simplest DSPy optimizer. You tell it what good means, which is a metric, how many examples it's allowed to add to the prompt. For example, here the max bootstrap demos is 4, and how many times to repeat the process, the max round. It won't touch your code or your signature. It only figures out which few shot example to inject into the prompt. So the optimizer.compile, here's the actual work. So you handed a fresh and trained classifier, which is student, and your trained data, the train set. Internally, it runs the classifier on every training example, finds the ones where it got the right answer, and promotes those successful input-output pairs into the prompt as demonstrations. It essentially asking which example which shown to the model make it most consistently correct. This is why it takes a few minutes. It's running many LLM calls behind the scenes. So now the optimized performance section. It's the same loop as the baseline, but now on the optimized classifier. The improvement line is the payoff. That data tells you how much the optimizer moved the needle. Then save, serialize the entire compiled program, the signatures, the chosen few shot examples, everything into a JSON file you can load in production without rerunning the optimizer. So compile is DSPy running, experiment on your training data to find the best example to bake into the prompt, so you don't have to guess which examples work best. So I'll just run this example. So here I have the Python deep dive optimizer, and I hope here I had the configuration already set. I will put it again and then run the optimizer. So again, why this run? What the optimizer again is actually doing, the bootstrap view shot is the simplest optimizer. It runs an unoptimized program on the training example, finds the case where it got the right answer, and uses those successful traces as a few shot demonstration in the prompt. It's essentially finding the best example to show the model to get consistent good behavior. There are more powerful optimizers like MI Pro, which also optimizes the instruction test, and Bootstrap Few Shot with random search, which tries multiple example combination and picks the best. For production system, you would use those. For the demo, Bootstrap Few Shot shows the concept clearly. So the optimizer now finished, and we can have a look into the improvement. The baseline was getting the sentiment right, but confidence calibration was rough. So we can see here 0.97 for the first selected test example, and for the last one is 0.97. The optimized version, as we can see here, is more consistent because it now has example in the context showing it what well calibrated confidence looks like. And we can see already here the score going up to 99% and also 98. Also, we can see here the saved JSON. So you can see how the few shot examples the optimizer and baked it directly into the program. You can load it, version it, deploy it. So do some kind of A/B test against a different optimization. And this is what compiled prompt means. It's a serializable artifact, not a string in your source code. So as we saw, DSPy is not always the right tool. Sometimes maybe the handcrafted prompting could do a little bit better than the DSPy. We saw how more sophisticated the prompting was better in the code review to some extent, but we can use DSPy when the task has a clear input and output contract. You know what the field you need out of the model. You are building pipeline with multiple steps where context needs to flow between them. You have or can create evaluation data and metric because without those optimizers can't do anything. You are building something you will iterate on. The investment in signature and modules pays off over time. So you need reliability, structured output, retry logic, consistent formatting. So we can stick with the traditional prompting when we are doing one-off task. So ask a question, get an answer, and done. So you need a maximum creative freedom here. The output contract of DSPy can constrain creativity in a way you don't want it. Also, in the case of you are prototyping and don't know what the output should look like, your team doesn't know Python well, for example. DSPy is a Python first framework. Traditional prompting is faster to start. You write a string, you call the API, and done. DSPy is faster to maintain. Changing the output format means changing a field definition, not hunting through prompt strings. Traditional prompting gives you full control over what the model sees. DSPy abstracts that away, which is usually good but occasionally frustrating when you need to debug a weird model behavior. DSPy optimization generally work. The benchmarks from the Stanford paper shows consistent improvement over handcrafted prompts on complex tasks. For simple tasks, the gap is smaller. The frame I keep coming back to, if you are building something that will be in production for more than months, DSPy is almost certainly worth it. If you are exploring, prototyping, or doing one off, write the prompt string and move on. So we built 5 programs today, a sentiment classifier that showed the direct comparison with traditional prompting, a RAG pipeline that handles out of context questions gracefully, a multi-step code review pipeline with automatic context threading, a React agent with real tool use, and we run the optimizer and watch DSPy improve its own prompts. The through line across all 5, you wrote data contracts, not instruction. You describe what the program should produce, not how it should think. And the optimizer, you define what better means and let the system figure out how to get there. Prompts are not your source code, they are compiled artifacts. Write the program, let the SPY write the prompt. Thanks for watching. If you want more of this, like the video, subscribe with notification on, and share it with your friends. We release new videos every week on AI development, agents, and developer tooling. Thanks for being here.